Let's look at some of the currents just to get a sense of each basin. So this is the annual mean surface current vectors in the Pacific Ocean. So you have obviously strong westward currents on either side of the equator, and the currents actually are going in the reverse direction here in this so-called north equatorial counter current, which we said is a gravity driven current from the sea level building up here because of this westward pushing water by the trade winds. And you see the gyre circulation here somewhat not completely as coherent as you would imagine. We'll see later on that ocean also has lots of eddies. So when you average over a long time, you think the currents are going straight up all the way from there to there, but actually there is a lot of eddies everywhere. Okay, and the Southern Ocean is obviously different, does have very strong coherent currents, but also lots of eddies because it's a channel. And you have the subpolar gyre here, so you have the clockwise here and the counterclockwise here, and you can see the difference also in terms of a strong Kuroshio current that's much more zonal here, but whereas in the Atlantic we'll see that it's much more towards the poles, northeastward as opposed to just eastward. And you'll see much weaker current here, as we said, because these western boundary currents are narrower, stronger, and deeper than these weak, broad, shallow currents. There is upwelling here and here as well, in addition to the equator, because the trade winds push water away from the equator here, but the trade winds also push water away from the coast, typically on the western boundaries of the coast of the land and eastern boundaries of the oceans. So eastern boundary of the Pacific Ocean here and here has strong upwelling, which is where you'll get a lot of chlorophyll and fish and so on. Okay. We'll look at the variability of these currents in various contexts. The other thing that's unique about the Pacific is that there is a direct exchange of water from the Pacific into the Indian Ocean through these Indonesian seas, which is called the Indonesian through flow, which we will run into when we do the so-called thermohaline or density-driven currents. The Atlantic, again, the figure is not so great, but I'll show another one later on. Strong western boundary currents can be seen here at low latitudes going into the Gulf of Mexico, squeezing between Cuba and Florida, coming out as Florida current, and then you can see that it does go zonal and then splits off into northeastward currents going all the way here. Okay, and you have a separate Labrador Sea circulation and the Norwegian Sea circulation and so on. So this place is special because of these warm waters coming all the way in here, as we will see. The unique thing about the Atlantic also is that it has exchanges with the Mediterranean Sea. Mediterranean Sea is unique as well because it is an evaporative basin, which means it produces some waters that are actually heavier than the Atlantic water that's going in. So the Mediterranean water actually comes out below the surface through this Strait of Gibraltar, and the Atlantic water goes at the surface, which is very unusual compared to most of the estuarine circulations. Red Sea actually has a similar situation anyways. Nonetheless, the salinity signature we had seen actually is related to this heavy Mediterranean salty water coming out. We again see the Southern Ocean being unique here. And there is upwelling here and upwelling here as well. There are also western boundary currents in the southern hemisphere. Obviously the same physics of the gyres and the western boundary intensification and the weaker, broader, shallower eastern boundary currents happen in the southern hemisphere as well. The the west coast of Australia is slightly different because of this water coming in here. this piles up some water here and creates a pressure gradient which can drive currents into the winds, as opposed to the currents going along the winds here in the Pacific and also in the Atlantic oceans. Okay, so there are very freaky features in each ocean. The Indian Ocean is very different. You can see that the currents are actually going from west to east, as opposed to the other oceans where they're going from east to west. But just like it doesn't make much sense to make zonal mean meridional sections in the ocean, it doesn't make much sense to do annual mean currents in the Indian Ocean, because the winds completely change direction. They go from the southwest to the northeast during the summer months and go from northeast to the southwest during the winter season. So the entire wind-driven circulation in the ocean changes. To the north of about 10 south, whereas to the south of about 10 south, the winds are more like the trade wind structures with the southeasterlies. But the addition of this water from the Pacific makes a difference as well. That water is coming out here, and some of it goes across into the Atlantic, and some of it retroflects back to the east and joins this Southern Ocean circulation. Okay, looking more specifically at a flow at about 700 meters in the Atlantic, you can see the strong western boundary current still here with some recirculation happening, and you see that the currents here have basically disappeared. This is the difference between the strong western boundary currents, which are deeper, whereas these are weaker and shallower. You also get western boundary currents to the north going in the opposite direction. This is going north, whereas these are going south. Okay, so you get the subpolar gyre there with the corresponding geostrophic pressure field. So if the currents are zonal from west to east, then Coriolis is to the south and pressure gradient is to the north. So you have high pressure, low pressure driving pressure gradient force that way, balanced by the Coriolis this way. So you have geostrophic flow field happening in this direction. So finally we are getting into some large scale balance in the ocean, which obviously looks different than the atmosphere, but nonetheless you get westerly currents as opposed to the westerly winds in the atmosphere, or parallel to the westerly winds in the atmosphere. So that's kind of a brief introduction. We will revisit this in different contexts, and we will set up the physics of the western boundary intensification, which is one of the most exciting topics in oceanography, actually, other than the thermohaline circulation. Okay.